Why will I learn Einstein's general theory of relativity? Will it improve my career? Will it secure a kind of a job prospect? Does this theory carry any significance in terms of my future prospect, securing a job or progressing anything regarding physics or mathematics? Most importantly, will it improve my thinking power? Well, for me and to all of you, the answer is a big yes, and that is the agenda of today's video. In today's video, I'm going to take you through a fascinating journey which will explore each and every aspect of this theory and will show you what are the career prospects, what are the jobs, what are the openings, what are the areas in which you can progress, taking Einstein's relativity further, the research scopes, and most importantly, as you have read in the thumbnail, yes, a little bit about deep learning. In today's video, we are going to explore and I'm going to show you the career and the job prospects, considering that you are venturing into a journey of learning Einstein's theory of relativity. My name is Shaunak and you're watching this video on Physics for Students. I welcome you to my channel. In general, if you consider the general notion of Einstein's theory of relativity is just limited to few people. Only a few physicists or mathematicians who really understand difficult tensor calculus, differential geometry can understand a little bit about relativity. It is a common misnomer that this theory really have no significance in terms of job, in terms of career, and anything which has got a day-to-day understanding and improving our lifestyle if we are venturing to understand relativity other than just satisfying our curiosity of knowledge. But it is not so. This theory of relativity has got an immense scope in terms of job, in terms of career, and in terms of our thinking pattern. Well, the root of Einstein's relativity is basically based on few of the principles. Take a quick look on your screen. So first of all, it is based on special relativity, non-Euclidean geometry, tensor calculus, differential geometry, and most importantly, critical or abstract thinking. Now, we are not dealing with special relativity definitely. As you see, I have marked the next 4 points in green. So we will look into non-Euclidean geometry first, and we will explore what are the career prospects, what are the areas that we can do, what are the job market of that. Then we are also going to look into tensor calculus and then into differential geometry, what are the industry applications and how we can secure a job. And then we will start with critical or abstract thinking. So first of all, let us start with what is called a non-Euclidean geometry. Now, those who already know about general theory of relativity, which I suppose most of you already know, the first thing that we need to understand is that relativity, or especially Einstein's general relativity or GR, deals with something which is called a non-Euclidean geometry. A geometry which is not flat, a geometry that doesn't follow the Euclid's postulates, but a kind of a non-Euclidean geometry which can be hyperbolic, which can be spherical, and most importantly, what we call as a Riemannian geometry. Now, coming back to what is called non-Euclidean geometry, first of all, we need to understand this. Nowadays, with the growing information technology, the internet is growing so fast, and most importantly, it has now become an integral part of our life, right? Social media, WhatsApp, Instagram, messages, sending messages across, in fact, the entire daily life, the moment we open our eyes till we are going to sleep, is all about internet information, reading those informations, and most importantly, linking those informations to the right point. Now, according to the internet world, the statistics says that more than 1,000 million people are estimated to use internet every day to communicate with each other. Online social networks, as I was telling, has become an integral part of human society activities. Now, the internet infrastructure as a result is severely stressed. Rapidly growing overheads associated with primary functions of the internet are increasingly becoming difficult, complex, and it is causing a concern among internet experts that the existing internet routing architecture may not sustain even another decade. Now, if the structure cannot sustain for another decade, then we need to find out a way, we need to find out a process in which internet or the connectivity or the routing process can be done in a very smooth manner. Researchers says that the Google, or when we are searching anything on Google, what is coming right on the first page, etc., are all because internet is considered to be a hyperbolic geometry. The first initiation of starting the career or getting into new non-Euclidean geometry is that internet is considered to be a hyperbolic geometry. Now, look into this figure, which I've just tried to show you, that the constantly changing structure of the internet leads to immense and quickly growing routing costs. The existing internet structure, as I was saying, may not last a decade. The very first question is that, right on your figure, as you have seen, I have just given some of the places in US. So Appleton, Alfred, and for example, Allagash and Andover. If I just give you these numbers, I mean to say for example, as you see, Appleton 23, Alfred 12, Andover 2, Allagash 1, all these numbers are given, then what happens exactly is that you will not find a kind of a route map. So from Appleton, if you want to go to Alfred, and from Alfred you want to go to Allagash, only 23, 22 or state over 24, state route 136, does it really carry any meaning? Really, you really are perplexed, complex, right? I mean to say, you're confused where to go, especially from one place to another. That is the problem. The internet nowadays has got such an immense traffic that if I just give those numbers, or the communication travels from one place to another, it becomes very difficult. So what is happening is that we are not given a kind of a map, just few numbers. Imagine that these are few numbers where we are transferring the data, and it is not possible. So in the next figure right on your screen, what you see is that internet being a hyperbolic geometry, what we need is a map. Now you see these are the blue dot points which are just connected. This is called network tomography. Now, if I talk of network tomography, it is the study of networks' internal characteristics information derived from the endpoint data. The question is that if we need a map in a hyperbolic plane or in a kind of an hyperbolic surface, what do we do? So study of networks' internal characteristics using from one point to another, that is called network tomography. It's a common kind of a term for network engineers. So now the question is that, given a kind of a hyperbolic plane, which the researcher says we don't have a route map to go, then how can we transfer data from one place to another? The answer is right on your screen. So there is something which is called an autonomous system. An autonomous system is a set of internal routable IP prefixes belonging to a network or a collection of networks that are managed, controlled, and supervised by a single entity or organization. And AS utilizes a common routing policy controlled by this entity. Here on your screen, you can see an autonomous system is a collection of internet protocol. The internet infrastructure is composed of connection between. To make things very simple, we have got an autonomous system, which is a collection of certain IPs, right, which will help us to transfer data from one place to another. That means we are in search of a map on an hyperbolic plane, which will help us to transmit data, which autonomous system is doing from one plane to another. Now you see right on your screen what is called this finding a path or a metric space X, so that the internet graph can be drawn in X, and that is the best path, which is called approximately using what is called a geodesic. Now, as soon as we use the term geodesic, you understand it is the shortest path between one place to another. Coming right now, what you can understand is that geodesic, we have dealt in general theory of relativity. We know these geodesics are the shortest path between two particular points. We have seen in my earlier lectures in general relativity, you have seen that the geodesic paths between one point to another in a plane or in a curve results in the curve of a curvature, which is called gravity. So here also the hyperbolic plane can be used to create what is called a scale-free network. That means we are now in search of something which is called a geodesic, which is a typical term which we have earlier used in general relativity. So in a hyperbolic plane, now you see the next figure which is right on your screen. If you zoom it a little bit, you will see these are the countries, right? Italy, Austria, Germany, France, UK and so on. And if you browse the blue portion, you will see that TDC, these are the technical terms, or these are the places where the autonomous system resides or where the connections are. So you see, I have given here that in fact it is possible to place the nodes of any scale-free network into the hyperbolic plane so that the shortest paths tracks geodesics. The size of the AS nodes is proportional to the logarithm of their degrees. I'm not going details into the mathematics, but the mathematics tells that if you consider a hyperbolic geometry, hyperbolic plane, which the internet is already, and if you consider connecting those nodes in such a way that the routing and the other costs are minimized, the network connections become smooth, the routers are placed at a particular, at a very comfortable position, and most importantly, the data loss is minimal, then we need to apply hyperbolic geometry, that is geodesics, construction of geodesic metric spaces from one point to another, and thereby we can get a kind of a scale-free or a smooth routing system of communication. So the first part is that if you're really learning general theory of relativity, you will learn hyperbolic geometry, you will learn geodesics, and as a result, you're already securing your job as a network engineer. By knowing this, you can design a kind of a route map which will enhance the communication. Will it really enhance the communication? What would be the advantage of using these geometry or mathematics on hyperbolic plane? That is coming up in the next part of this video. Constructing internet as a hyperbolic geometry. Once we have constructed an algorithm which uses or finds of geodesics and we have planted those routers over there, what will happen? Right on your screen you see that it produces a routing algorithm which is 97% successful. It reflects geopolitical boundaries. It does not cause abnormal traffic congestion. It is unaffected by random removals from the graph and has limited performance degradation over time. When I say random removals from the graph, I'm trying to tell you that if I just pick up those points in terms of the geopolitical boundaries and I remove those nodes particularly, then what happens is that it remains unaffected. That is the beauty of hyperbolic geometry. So I hope right now what you can understand is that learning relativity, especially hyperbolic geometry, learning geodesics, first secures your career into network engineering, secures your career or get kind of a job where you can design this kind of an algorithm, and you are doing something which is directly related to Einstein's relativity. Do you know what kind of prospect would be? That would be in the next part of the video. Talk of this non-Euclidean geometry, another prospect which comes is a kind of a map making and measuring distance on a sphere. We remember that when we are measuring the distance from New York to Japan around the sphere, what we are using is basically non-Euclidean geometry. Let me quickly demonstrate you with a figure right on your screen. As you see, the surface of a sphere is not in Euclidean space. Measuring distances of the sphere, map making, and most importantly, when you zoom something on Google, I mean to say when you are using Google Map, when you're zooming in, zooming out, how does it happen? How does it happen? It really happens through hyperbolic geometry. The technology that we use on the Zoom or on Zoom Map or on Google are all because we are trying to phase in and phase out, zoom in and zoom out. What? It is the sphere, it is the earth that we are trying to find the location and places. And obviously earth is basically a non-Euclidean space. It is a kind of a sphere, and on the sphere what we operate is non-Euclidean geometry. So from this part, I hope what the first part of the video is clear, that if you are really into relativity or learning hyperbolic geometry, non-Euclidean geometry, geodesics, straight line paths, then the jobs that you get is that of a network engineer, software engineer, designer, etc. And that is indeed very, very, very fascinating. The next question which comes to our mind is that all? Is that all that we get in non-Euclidean geometry as a job, or are there certain things which we can further explore? Let us find it out in the next part of the video. That there is a life without computers, MRI, EKG, ECG scans, etc. It has been done. American professor Stephen Casey, chair and professor of mathematics in the American University Department of Mathematics and Statistics, actually has calculated the hyperbolic geometry, the internet as an hyperbolic geometry, and he has actually shown that information is gathered, stored, and communicated in this hyperbolic plane. His research involves tools from many areas, including harmonic and complex analysis and integral and differential. You see, if I consider Poincaré disk or the famous MC Escher's drawing, then what happens is that all those monsters, if you really remember, so we are trying to fit in a huge amount of data in a small space, which is the hyperbolic plane. In internet, exactly that is the problem. When we are talking of the routing cost, etc., what is happening is that so many routers, so many internet has clogged us that we are really in dearth of place. Just imagine of YouTube every day, so many huge amount of trillions of data are being uploaded. How YouTube is keeping those data? That is the beauty of doing hyperbolic geometry, right? So just in a Poincaré's plane or in a hyperbolic plane, we are trying to fit in huge amount of infinite information in a finite plane. Professor Casey's research shows that internet can fit in huge amount of data. That's a good news in a kind of a finite plane, and hyperbolic structures actually enables us to do that. So Professor Casey's actually kind of a report shows that yes, it is possible. The research says, everything says that it has been done. Now it is our step that can we go ahead and design that kind of a network. There's something which is called a perspective drawing, right? So perspective drawing is a kind of a technique that gives the illusion of spatial depth or perspective to drawings. Let us find out in a quick figure. Right on your screen, you see that this first one is the art or mathematics of realistically depicting the three-dimensional objects in a two-dimensional plane. So you see the first one is a one-point perspective, then there's a second-point perspective, and there's a third-point perspective. Perspective drawing is something which is very, very, very important, and this perspective drawing is basically, drawing a three-dimensional kind of a figure right on a one-dimensional, on a two-dimensional figure, and it has got a lot of implications. Let me show you what are the career options if you really know perspective drawing and non-Euclidean geometry that can come up. Here on your screen, you can see interior designing, CAD engineering. You can also become an animator, cartographer, most important. I mean to say those who really measures the distances and does thing with the earth and measurements. Game developer, yes, because as you see that when you're developing a computer game, especially on a three-dimensional surface or any kind of a complex surface, then you need to know non-Euclidean geometry. You need to know spherical, hyperbolic, or other things. Mathematician, obviously, I mean to say, let us not elucidate on that. Robotic engineers and architects. I remember around about 2 years back, one of my subscribers, his name is Gagandeep, residing in London, looking into one of my lectures in differential geometry, gave me a call and told that I am really looking into differential geometry because he's an architect. So what he does is that he studies those different curved surfaces and then models it over the computer on a three-dimensional, and these models are then being designed either on a office or on the roofs, etc. So game developer is a very important aspect because all these the recent games are fascinating, uses complex structures, so the knowledge of non-Euclidean geometry is very important. Architects are equally important. CAD engineering and animators is definitely one of those parts. So first aspect of non-Euclidean geometry, learning non-Euclidean geometry, securing job as animators, 3D, three-dimensional engineers, networking engineers, and most importantly, how internet, considering it as a hyperbolic geometry, you can do a lot of job has already been secured. What is the next part of the video? What is the next job that is coming up? Do you remember? Let us find it out in the next part of our video. Whenever we are thinking about Einstein's general theory of relativity, the first thing that crops in our mind is what? Tensors, right? Question of tensors, learning tensors, tensor calculus, internet is full of huge amount of data in tensor. The question is that what are the real life applications of tensor? Let us find it out, and let us also find it out what could be the next jobs that promises us if we learn tensor. So right on your screen, let me show you. So engineering is an integral part which uses tensor. Elasticity, deformation of elastic bodies, electrodynamics, continuum mechanics, almost all engineering analysis can be done through tensors. Fluid mechanics and a lot, and the last contains a lot into deep learning and machine learning, which we are going to explore in this part of the video. So I'm not saying that general relativity is the only subject which deals with tensors. Classical mechanics even have got tensors, electromagnetic tensor, there are a lot. But as you say, there is a famous old saying, if I remember rightly, that is called the more you bleed during training, the less you bleed during war. So the more intense is the process of learning tensors, calculation, Einstein summation, indices, etc., then what will happen is that the less you bleed in war, that means the jobs and other things will become more secured. This is exactly what Einstein's general relativity does, because all the field equations, the entire edifice of relativity is built on tensors. So you really learn a lot into the tensors. So I would like to show you a few more points here on your screen. All of engineering analysis makes use of tensors at the fundamental level. Computational and fluid dynamic loads are also used in tensors. So it goes without saying to anybody that tensors are the most important part of relativity, and tensors have huge amount of industry applications. And if you really know tensors very well, then you secure a kind of a job. Let me show you on a figure what are certain other important things. So here you see there is something which is called a stress tensor. So if you are really measuring what is shown, elasticity and deformation of elastic bodies and other stress or stress energy tensor, which is a stress energy momentum tensor, then you can do that. If you're really good in tensors, then you can become, or you can secure a job in fluid dynamics. And there is something which is very emerging but a very technical field, which is called diffusion tensor of MRI. Let us find it out in the next part of video what this is all about. Although it is a very technical term, but still I would like to explain to you, it is a kind of a diffusion process which in general in physics happens, and it helps us to know, or I would say it helps us to know more about the brains or anything that we are scanning, which is far more better than MRI. Let me show you right on the screen what it is. Here you can see the diffusion tensor is a magnetic resonance, and its studies are increasingly popular among clinicians and researchers as they provide unique insights into brain network connectivity. So diffusion weighted imaging is a variant of conventional magnetic resonance imaging, which is called an MRI, based on the tissue of a very high-end technology which uses no equipment. There is no contrast agents. That means, for example, you are pushing a dye in your body in order to get a kind of a contrast, which is usually done, and no chemical tracers. So the introduction of the diffusion tensor model enabled the indirect measurement of the degree of anisotropy and structural orientation that characterizes the diffusion tensor imaging. I was reading a lot, but because I'm not coming from a medical background, I cannot understand a lot. But if you are watching this video and if you're coming from medical background and you know really what is diffusion tensor imaging, put a little bit more into the description box or in the comment box. all of us, we are willing to learn if you really know about that. So the first part is that using tensor analysis, using those what you call eigenvalues and the tensors, we are now into a better process to know and detect cancers, white matter of the brain, neural networks, etc. And that is coming from the integral part, that is the knowledge of tensors. Also, tensors are used in wireless communication. Just have a quick look on the screen. Now, this is again too technical. Tensor decomposition in wireless communication and MIMO radar. So I will give you this research link right in the description box so that you can see. So you can see there is something called a Tucker decomposition of the third order tensor and illustration of the BTD models. All these, are using tensors. Now, I mean to say, for example, in wireless communication, when we are trying to establish a better wireless communication, then tensors are being modeled. Now, as we know, there is a zero, which is a scalar, the first order tensor, the second order tensors, and so on. So the decomposition of the tensors in general, what we learn in tensor operations, are being used in order to communicate things. That means the wireless communication or the model of wireless communication that are being designed are using the properties of the first, second, third order, or maybe n-dimensional higher order tensors in order to establish communication. This is highly technical, to be very honest, and this is not the right place to explain a lot, but tensors and their applications, starting from MRI scan and going up to wireless communication, are still there. Now comes the most important thing. What is the current use of tensors in terms of internet? The way we are talking, the way we are using Facebook, the way the things are moving around in YouTube and coming suggestions. So is there also an element of tensor analysis which is being used in a day-to-day life, in social media, Instagram and others? That is coming up in the next part of our video. This is awesome, and this requires a special attention to make up a video. First, let us understand that what is deep learning. Now, before I go into the sketches and programs, let us understand that deep learning is a part of an artificial intelligence, or I would say it is a kind of a subset of machine learning. So what it does is that instead of going or feeding the machine with the data, which is a kind of an input-output, it feeds the data in such a way that the machine or the computer or whatsoever starts thinking more as a human being. Now, this sounds odd. I will just explain you what it is. Have a close look in the screen. Deep learning is a subfield of machine learning concerned with algorithms inspired by the structure and function of the brain, which is called artificial neural networks. So it mimics the human brain and makes predictions with incredible accuracy. That means instead of going further a step ahead into artificial intelligence, we are feeding the computer or the system with such kind of a data that it will maybe someday touch or feel or mimic as a human being. In order to give you a quick perspective, right on your screen, you can see artificial intelligence is basically the wholesome approach, then comes machine learning, and then comes deep learning, etc. I'm really fascinated to make another video which is dedicated to deep learning and tensor applications. Let me give you a very quick understanding about what is deep learning in just 2 to 3 minutes time. Look on your screen. What I'm trying to tell you is that there is a kind of a tomato and there is a cherry, right? Almost looks similar, but when we are trying to feed in the data to the computer that, okay, this is tomato and this is cherry, what will we do? If it comes to machine learning, which is the earlier part of deep learning, then we will say that are the features. So this will be a little bit more round, this will be a little bit more reddish, it will carry a stem which is longer, it will carry a kind of a not longer stem. So what we are trying to tell is that we are involving certain features in the machine, and once the machine identifies the features, it will tell, okay, this is tomato and this is cherry. What happens with deep learning is that we are not feeding the data in terms of features. We are feeding the data just as human brain thinks. So that is why you see on the screen that first one is what is called distinguishing features, and the second one is called neural network. So what happens is that when neural network, I'm not going too much into the first layer, input, output, those things, but what happens is that when you feed the machine with neural network, then identification becomes much more easier. In the screen right now, as you can see, that tomato and cherry, if we really need to feed that, then what we need to go is that we need to give more and more and more or more of pictures, photographs, or simulations, which will be something similar, which the machine can understand that okay, this is tomato, this is cherry. So that is why I have written that it needs to feed the data or machine with much higher volume of data. Because if you use the feature part, then it might match, it might not match. It requires a lot of input output and lot of complex programmings. But if I can always show, and the machine can understand that okay, so this is tomato, not from the features, but just as the way human neural network works, then that becomes easier. So the question is that when we are feeding enormous amount of data to the machine to get a quick understanding of the system through neural network, just as human brain does, then the question is that how can we feed those data? Look on your screen. The next part I have shown that, for example, if you pick up a tomato or any kind of an illustration, it contains a 28 by 28 pixels, which come to 784 pixels, just one particular image. Now think that the enormous amount of data that we are trying to fit to the machine in order to make it more better in terms of AI, artificial intelligence, and have a neural networking kind of a thinking. Huge amount of data needs to be fit up. What is the answer? The answer are tensors. If you have, we have discussed right at the beginning that a huge infinite data, when we're trying to fit it on a finite place, that is what hyperbolic geometry does, and the method of the technology through which it happens is basically tensor. You see, what I'm trying to show you is that this TensorFlow and PyTorch, these are libraries and are deep learning frameworks. I mean to say, what is going to happen is that if you really search over the internet and other areas, you will see that tensor, when you type in the word tensor, the immediate first thing that Google show is TensorFlow. Now, what is the TensorFlow? TensorFlow is basically kind of a library which is developed by, I think, Google Brain, which helps in programming. Now, you see that learning tensors actually would help you in machine learning and deep learning. On your screen, if you zoom a little bit more, then what you will see is that this is a kind of a Python Python algorithm which shows import NumPy and then tensor ending. So what I'm trying to show you is that Python, the programming language, is importing NumPy, which is a kind of, we will just see next what is NumPy, and it is constructing through the use of programming language tensors. So you will see it is a 1 by 1 tensor, then a 2 by 2, 4 by 4. It just takes the shape of a matrix, just like linear algebra we used to do. It is obeying the same kind of an algorithm. So learning linear algebra from their matrices, from their tensors, will actually help you to learn a lot about machine learning and deep learning. It is the, I would say, trend now, the future, with huge amount of salary which is gaining, and a lot of my students, etc., are going to learn deep learning. But what is the essence? The essence is that if you really learn tensors, and if you use the Python in order to make those tensors, so that huge amount of information which is being used by the system in order to make deep learning, in order to make a better artificial intelligence, that will be reflected, that will be done. So tensors are actually the data structure used by machine learning, and getting to know them is an essential skill which you can build on. And tensor, as we know, mathematical tensor is also container of numerical data, and it is the way we store the information. So you can see that it is a 4 by 4 and other things. So now the question is that we have been talking about tensors and something which is called Python, and there is something which is called NumPy. Right. So we have already understood the root map, linear algebra, matrices to tensors. Tensors whole helps us to store a huge amount of data. Using deep learning, we are feeding the machine with the artificial intelligence neural network system so that it can understand pattern and recognize pattern, not through features but through the imaging of the data. And how we can do that, that is done through tensors. The question is that we are using NumPy or anything related to Python programming language. What is that? That is coming in the next part. Deep learning uses tensors to make calculations faster. Right on your screen, NumPy is a general purpose array processing package. It provides a high performance multi-dimensional array object and tools for working with these arrays. And deep learning, because we need a performance to compute a lot of matrix multiplications, hence we use tensors. Now we know that the matrix calculations and the imagings are so intense that this is being stored in GPU or graphical process unit. We know about CPU as well as GPU. So all these things are being stored now in GPU. So let me quickly repeat before we go into the next part of our video. That is, you must be wondering what are the jobs in deep learning. I am coming to that. But the basic thing is that understanding hyperbolic geometry, then going into tensors, and then going into deep learning immensely helps you, because all those information which needs to be fed in to the machine in order to make the machine behave more smartly, just as human brain does. That is what tensors are, and that is what deep learning is. So now I hope you understand, learning tensors, especially from general theory of relativity, secures a huge amount of current trending job. Deep learning, machine learning, TensorFlow, etc. TensorFlow also you can learn, and there's a huge market of TensorFlow because that is a product of Google. Question is that what are the jobs that I can get if I learn deep learning? Coming up in the next part of our video. I won't read it out. You can just take a pause and quickly take a note of what are the jobs in deep learning. So deep learning engineering, machine learning, senior AI engineering, deep learning expert, software engineer, research analyst. So the list is endless. So the thing is that deep learning has become important because you see in Facebook, whenever you're searching something, immediately the Facebook gives back the type of choice you want. Instagram, the type of choice you want. Gallery, I mean to say photograph stored in our mobile galleries. Once you take a photograph in Bangalore, it shows gallery in Bangalore. Once you take a photograph in Niagara Falls, it shows Niagara Falls. You take in Sweden, it shows Sweden. So the entire amount of information which are coming nowadays in computers, social media, I think that we are so much attached to a mobile. That is because it is now no more a mobile, it has become a human being. It is interacting just like our friends or colleagues, somebody whom we love, somebody whom we really want to talk. And why is that? Because artificial intelligence or deep learning is becoming so important, and entire machine and everything is behaving almost like a human being. So friends, I would say nowadays mobiles are more friends than human beings, and that is the power, that is the win over of deep learning. And deep learning, because we need to focus and store a huge amount of data, that is why hyperbolic geometry, that is why machine learning, that is why tensor analysis. So we are done with this part of the video, that tensors, applications, deep learning, how it helps, what are the jobs that we can get. It's a very highly paid job, and it's a very, I would say, a kind of a glamorous job. What are the other areas of general relativity that we can explore? Let us find it out in the next part of the video. Differential geometry. Well, the applications are huge. I need to make a separate video on differential geometry. But differential geometry, which is a kind of an applied mathematics tool, helps a lot and secures a lot in terms of job. Abstract designing, as you can see, these figures, etc., shows designing structures, etc. And right on your screen you can see a few of the applications, starting from electromagnetism, robotics, quantum field theory, chemistry, engineering, and so on. So I won't elaborate too much, otherwise the video itself has got certain more relevant points to clear. Differential geometry, again, I remember a lot of people In fact, I know a lot of subscribers who have subscribed to my channel. I have been talking to them over WhatsApp, audio, phone calls, and chatting them over. They are really keen to learn more about differential geometry because they are architects. So the question which comes next to our mind is that what are the jobs? What are the type of jobs that we can secure if we learn differential geometry? Let us find it in the next part of our video. Quick list, you can just take a note of that if you want. Senior manager, analytical insights, data scientist, designer, data modeling, and so on. So just in all, differential geometry is a particular subject which deals with geometry. These deals with structure, curved spaces, manifolds, etc. So starting as an AutoCAD designer, engineering, interior designer, interior structural designing, even if you're using going into bank and you're studying huge amount of data, analyzing those data, keeping it in the fold, differential geometry will definitely going to help. Tensors are being done. I mean to say, first we started with non-Euclidean geometry, hyperbolic geometry, then we moved into tensor applications, completes the second part. Third, differential geometry using structures and even into molecular genetics. What would be the next part of the video? Find it out right now. There is a subtle difference. Would we call it as a critical thinking or an abstract thinking? Let me give you a very subtle difference, a quick overview. See on the screen. So critical thinking takes background knowledge to form a decision. Abstract thinking is seeing things in a way which could be more creative, but in patterns that might be disconnected. That means if I consider critical thinking, so we are given a kind of a condition and then we critically analyze whether it is right to go or not. So that is called a critical thinking. Abstract thinking is something which is much more constructive, but those patterns and those structures are really disconnected. So I hope you got the answer that in general theory of relativity, what we do is more of an abstract thinking because things are not more connected between tensors, geometry, differential geometry, manifolds, etc. And we are trying to get in a kind of a conclusion. This is the last part of the video, but most important is that how general theory of relativity, apart from securing jobs in deep learning, tensor analysis, MRI, medical, etc., how does it really help in our thinking process? Now that we know that we are into abstract thinking, this is very important. Before we start, I would like to tell you that general theory of relativity, I think, should be in some part put into undergrad or at least in school days, in the schools. Because Einstein is a very iconic figure in West, if you go in US, etc. People really want to know more about Einstein. So their young people are taking a plunge into tensors, I mean to say Einstein's work. But I'm afraid to say that is not happening as far as India is concerned. So abstract thinking is something which all parents should enhance, or I would say should encourage their students to do, because abstract thinking at a very early age involves a lot of productivity. First, on your screen, the power of abstract thinking increases the power of imagination. So obviously when you're imagining something which is not very concrete, which has got certain things which are very abstract. So engineering, nuclear physics, cosmology, and quantum mechanics, these are the areas, or I would say these are the job prospects or career areas where you can move if you have a very good abstract thinking. So abstract thinking not only makes your brain fertile, but it also secures a job. It also secures a kind of a better career. So first of all, it increases the power of imagination. Next is that it helps us to understand patterns and structures. So when we are thinking of a 4 or a 5-dimensional thing, we really cannot comprehend what is a 3-dimension, no, what is a 4 or a 5-dimension, n-dimensional manifold, n-space vector. What are those things? These are abstract things. So if you're starting at a very early age and start thinking more about abstract thinking, I think you will grow up the ladder much more. So designing and structures, so it comes to differential geometry, tensor analysis, anything, understanding of structures are very difficult if you really don't have the power of abstract thinking. So designing, structuring, and architecture, this is a very, very important area that you can explore if you have a kind of an abstract thinking. Then comes the power of abstract thinking: create or generalize structures on a broader rule. So we have seen that you can become a database administrator, you can become into machine learning, artificial intelligence, because you are generalizing it on a broader rule. From machine learning, which is restricted to a certain pattern structures of artificial intelligence, you are generalizing broader into deep learning. You are feeding the machine with more data so that through structures and other advanced technology, they can react just as neural network does, human brain does. And also quantum computing is something where we are using recent researchers and Nobel Prizes for Allen aspect shows that we can use the spin or the quantum entanglement to use quantum computing. That means we are generalizing those scientific discoveries on a much more broader scale. Ability to link geometrical representation, obviously deep learning, AI, cosmology, the geometrical learning that you have got, you have the ability to link it for direct applications. Next comes, you develop a kind of a mathematical intuition. Obviously with maturity, research, analysis, handling large-scale data, you develop a kind of a mathematical maturity. This maturity helps in every aspect, be it an equation or research analysis, because even if you see a system, you can give a possible answer or solution. All these are done. All these are powers of exercising abstract thinking. What could be that it really helps into coming up in the next part of our video. A quick list on your screen. Arts definitely is something which is related to abstract thinking. You cannot draw an art by just having calculations or calculus. Computer science, lot of data modeling, etc. has helped in making computer models. Mathematics, I don't need to tell. Music, most importantly, because I really play piano, so I know how abstract thinking and the concept of melody and tunes and rhythms helps us in music. Neurology, it has helped because abstract thinking the scientists are using in order to develop further. Philosophy, obviously the entire philosophy, mathematical philosophy, Vedanta, everything is dependent on abstract thinking. And recent researches shows that social theory is also something which is based on abstract thinking. So the question is that abstract thinking is something which has really is a kind of an exercise that you need to do. It won't develop in a day. It is not that you've got a huge belly fat and you do 100 crunches in a day and within 5 or 7 or even 10 days your belly fat is reduced. No, it is a constant matter of exercise. And general theory of relativity is such a theory, considering others obviously, that induces and helps in huge amount of abstract thinking. So now we have seen that how abstract thinking not only secures a job but improves and increases the brain capacity up to any. Concludes our video as I do a kind of a quick summary. Most importantly, let us remember that general theory of relativity is not a diploma or a degree that, hey, come on, I've got a diploma, I've scored more than 90%, give me a job. It is not like that. General theory of relativity is a theory which encompasses a huge spectrum of other things which are being concerned. Concerns related to differential geometry, tensors, deep learning, AI, medical science, computing, computer engineering, network engineering. So I won't take our time again to, carry a summary from one by one. But what I wanted to tell you that this video, I hope I can make things clear that why you should take up general relativity, because it starts with Euclidean space. We started with special relativity, but that is not important. We started with Euclidean, non-Euclidean space, and we have shown that in computer science and especially the way things are turning up, the way things are growing in terms of increased network, routing costs, etc., non-Euclidean geometry helps. Researchers have shown, Google searches have shown that internet is hyperbolic space, so the geodesics and other things will come to much use. Then we came to tensor analysis, a huge amount of impact in industry, starting from using deep learning, artificial intelligence, thermodynamics, into general, what you call engineering, fluid dynamics a lot. We went into tensor analysis. Then we delved deep into deep learning, how tensor analysis really helped. Then finally we went into differential geometry. We showed that structures, architectural designing, a lot of jobs are there. And most importantly, critical and abstract thinking. How does it really help in order to move ahead in terms of thinking pattern, and exercising that would require time. So I would request that you can start thinking on abstract thinking right from the day one. Thank you for watching this video. Do put up your comments, like, and let me know what are the other areas that you think that you can put up or contribute in terms of job and prospects of differential geometry or any other field for learning general theory of relativity. Thank you for watching this video, and I wish you all the best, and I encourage you for this particular theory, general relativity, to learn, because I have just shown you that the chances of job and prospects are sky high.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.